Okay, so now we're going to go on to the second portion of being able to talk about SN2 reactions. And these are all the sort of different factors that you want to consider when you're thinking about SN2 reactions. So the first one is, how does the branched aspect of your alkyl halide, whether it's primary, secondary, tertiary, play into an SN2 reaction? Okay, so specifically, we're talking about how fast an SN2 reaction. So remember, what has to happen? A nucleophile has to come along and do a backside attack. Well, what do you think? Which one of these reactants do you think is going to be the easiest to attack from the backside? This has to do with steric hindrance. So what we see in terms of our reactivity is that a methyl is the most reactive in SN2 reactions because the carbon is only bound to hydrogen, so it's not at all sterically hindered. Primary, secondary, tertiary, as we go from primary to secondary to tertiary, all we have is more and more steric hindrance around that alpha carbon. So in terms of reactivity of SN2 reactions, tertiary are incredibly slow to the point where we actually consider them to be unreactive in SN2 reactions. And then a secondary is much faster, much slower than a primary and much slower than a methyl. Okay, we can look at these, numerically. See what's up here? This is specific to this reaction here where you have an alkyl halide and your nucleophile is an iodine that's in acetone at 25 degrees Celsius. These rates are specific to this particular reaction, but nonetheless, we can generalize this to all alkyl halides and all nucleophilic attacks. What we see, so we're going to do this all relative to this ethyl bromide or 1-bromoethane. Okay, relative to that, methyl bromide, or 1-bromomethane or bromomethane is 145 times faster in these SN2 reactions than our primary, right? So this would be methyl. This is a primary alkyl halide, secondary, tertiary. We get to a secondary, you're talking about like 0.8% of the rate of a primary, which is considerably slower, but in the grand scheme of chemistry, you got time, you can wait a little bit, right? So it's not like this reaction doesn't happen at all. But then when you get to a tertiary, we say that that's just negligible. It doesn't happen at all. It's so incredibly slow as to basically not occur. Okay, so steric hindrance leads to slower SN2 reactions. And that's the case even if there's substitution on the beta carbon, right? So again, we have this bromoethane, that's our reaction rate of 1. If we put a single substitution on it, so this would be, right, this is versus 1-bromopropane. And I will say, I haven't really been too much of a stickler on it, but we actually wouldn't include the 1 for bromoethane because it's always going to be position 1, right? Even if you put it on the other carbon, then you would just change how you numbered it. So when there's like an unambiguous location, you don't actually include the number. To me, it's not the greatest sin in the world. I'm much more concerned about you being able to name things with all the other rules going on, but just FYI, you won't see it. So anyways, we're going to compare bromoethane with bromopropane. 1 versus 0.8, so about 80% of the original reaction rate, pretty much the same. We'll call those pretty much the same, right? So if it's a straight chain alkane, it reacts all with pretty much the same rate. As soon as we branch that beta carbon, things then change quite dramatically. I'll point out, notice how branching on the alpha carbon, or rather a 2-carbon branch on the alpha carbon, has a much more of an impact than it does if you do it on the beta carbon. But nonetheless, again, it's the next door neighbor. The nucleophile is only attacking this carbon here. right? So it's all about, again, just steric hindrance. Even if there's substitutions on the beta carbon, it will have effect on the ability of the nucleophile to get to that alpha carbon. And then likewise, if we make it, put 3 branches on that beta carbon, then it gets to be quite slow. We don't say that it doesn't happen at all, right? It's not in that negligible category. But nonetheless, if you're going to compare the reaction rates of these 2 different alkyl halides, and one of them has a lot of branching and one of them doesn't, you can safely conclude that the more highly branched one is going to be slower. All right. So now let's sort of summarize this, or I guess illustrate this using our reaction coordinate diagrams, right? So let's just remind ourselves of what exactly these are. On our y-axis, we have potential energy, or more accurately called free energy. We start out with our reactants. They increase in energy as we reach our transition state, and then decrease till we get our products. In this case, this is an illustration of an exergonic reaction or a spontaneous reaction. At the tip here, we have that transition state. Those are those bonds, half broken, bonds half formed. And these are going to be, your transition states are kind of like indicated with that double dagger symbol you'll see a lot. And again, notice that there's this backside attack, which means we have this planar transition state. And then in terms of our diagrams, so which portion of this diagram corresponds to the thermodynamic favorability? That would be the distance from our reactants to our products. So this delta G. But what about the kinetics of this reaction? Remember, that has everything to do with the height of this barrier here, your activation energy. All right, so now I want to draw free energy diagrams that compare what happens with a methyl substrate to a primary to a secondary. And in all these, we're going to say that the reactants our reactants and our products are at about the same free energy. All right. It's a decent approximation because the bonds that are being broken in each of these reactions are a carbon halogen bond. And the bonds that are going to be formed are a carbon nucleophile bond, right? So same bonds are being broken, same bonds are being formed. You can look on that bond association energy, and you can point out that there is some difference, for example, between the strength of this bond and this bond. But broadly speaking, they're very, very similar. So we're going to say that all these reactions begin and end at the same place rather. And so then how can we illustrate what goes on with these reactions in terms of their rate? Remember that the methyl are going to be the fastest, and the secondary are going to be the slowest. So how can we illustrate that using our reaction coordinate diagrams here, our free energy diagrams here? That means that the big difference between these reactions are going to be the height of that activation energy barrier. Right, so going from methyl to primary to secondary, what we're really seeing is an increase in that activation energy. And then tertiary, which we say doesn't happen, so maybe that's just like all the way up here or something like that, some ridiculously high barrier that just can't be overcome. All right, and again, remember, like, why do we bother doing that? Remember, these free energy diagrams are a way that we can illustrate certain features of a reaction. So for example, comparing these reactions by their rate. So that's something that you're going to be doing in this chapter a lot, is drawing these free energy diagrams to compare what happens in this reaction to this reaction. Okay, so sterics, super important factor for SN2 reaction. The more sterically hindered that alpha carbon is, the slower it's going to occur. And if you get to the point where you're like a tertiary alkyl halide, it's just not going to happen at all because it's too sterically hindered. The next factor that's important is the strength of the nucleophile. Okay, so we haven't talked about nucleophile strength yet. We've sort of only broadly categorized this is a nucleophile, isn't a nucleophile. So now we're going to build off that a little bit and talk about nucleophilic strength. A strong nucleophile is, for example, a hydroxide. It's got this negative charge. It really wants, right? I mean, nucleophiles are electron dense species. It's got a lot of electron density to share. So this would be an example of a strong nucleophile. Weak nucleophiles will undergo SN2 reactions very, very slowly. So a weak nucleophile would be, for example, water compared to the strong nucleophile, the hydroxide ion. Okay. Bottom line, SN2 reactions need strong nucleophiles. So let's look at some examples of some strong nucleophiles versus weak nucleophiles. Let's look at weak nucleophiles first. So these are, for example, water or any alcohol would be considered a weak nucleophile. Another thing I would put in this category would be if you had an ammonia or a primary amine. This would also be considered a weak nucleophile. That's not enough bonds. So there needs to be two different groups on there. Primary or secondary amine would be considered a weak nucleophile, right? So basically the main feature here is that they have electrons to donate. It's either going to be an oxygen or a nitrogen, but they don't have a net negative charge, right? So their willingness to donate those electrons isn't quite as much as it would be if, for example, it had a net charge, like for example, a hydroxide ion, or this is a deprotonated alcohol. Notice, right? This would be the symbol for an alcohol. So I get rid of that proton, becomes just this negative charge. This is what's called an oxide ion. Other strong nucleophiles that we have are halogens, right? These the halide ions. They also have pairs that they can donate, and they have that negative charge. Introducing a few new ones, we have these sulfur-containing groups here, right? So these sulfide ions, and then also kind of randomly that we're going to consider in this class would be the cyanide ion. Okay, so bottom line, if it has a net negative charge in electrons, we can roughly consider it to be a good, strong nucleophile. If it has electrons to donate but doesn't have that negative charge, it's a weak nucleophile. All right, so sterics, important for SN2. Strength of the nucleophile, important for SN2. Now let's talk about how solvent plays a role. There are two different types of solvents. We're going to categorize these into two different broad categories. One is protic, meaning it has hydrogens, meaning it can hydrogen bond. And I guess more specifically, not just that it has hydrogens, but that it has hydrogens bound to a more electronegative atom and thus can form hydrogen bonds. So those would be protic solvents versus aprotic solvents. And these aprotic solvents are still polar. They're polar aprotic solvents. But so, for example, acetone is a common one that is considered to be polar. You have dipole-dipole interactions, but just no hydrogen bonds. Remember, hydrogen bonds are really just the strongest way in which molecules interact. That's why we're sort of doing these categories. The other big ones would be DMF, dimethylformaldehyde, formine, and DMSO. And DMSO in particular. The reason is because, you know, this DMSO looks a lot like acetone when you're first looking at it, until you remember that sulfur and carbon aren't in the same column on the periodic table. And so if you go through and do the Lewis structure for DMSO, you will find that your sulfur, in addition to having that polar bond, also has this pair of electrons on it. DMSO is about as close to the polarity of water as you can get without being protic. Acetonitrile, fine. This thing, I've never even heard of in my life. Probably important somewhere, but anyways. These are the big ones that I think you should really try to remember: acetone, DMF, and DMSO. So what's the big deal? Who cares? What's the difference between protic solvents and aprotic solvents? again, it has everything to do with this hydrogen bond, and specifically the hydrogen bond's ability to stabilize anionic species, or cationic, really just charge. So actually, yes, let's just call this charge. Protic solvents stabilize charged species better. Okay, so what does that mean for our reaction? Well, let's just take this potential energy diagram here. What's important to remember is that, let's just do a simple little example. This is going to be our right, so here's an example of a SN2 reaction. Here's my nucleophile. It's my alkyl halide. Well, SN2 reactions occur because you have a strong nucleophile, right? One of the defining features of a strong nucleophile is this net negative charge. So let's say that we're carrying out this reaction in a protic solvent like water, and we have this potential energy diagram, or this free energy diagram here. Well, what's going to happen if I change it to an aprotic solvent? Remember, what does a protic solvent mean? It means that it stabilizes that negative charge. So if I change it to an aprotic solvent, it's going to destabilize that negative charge, which means that my reactants are going to actually start off at a higher free energy than they would in a protic solvent. So aprotic solvents are actually great for SN2 reactions because they destabilize that nucleophile. So look at how much tinier this activation energy barrier is to overcome in an aprotic solvent than it is in a protic solvent, right? So if you really want to push this reaction forward, it might not sound like it, but destabilizing your reactants is a good thing.